In this previous video lecture, we'll talk about continuous random variables and densities. And here's the time for us to make precise the difference between continuous and absolutely continuous. Okay, a random variable x, it is continuous if its distributions assigns measure 0 to every fixed number x in R. So if you want to think in terms of the cumulative distribution function of x, so let's put t here and fx of t, continuous means exactly there are no points x that are assigned some positive probability. This is what it means to be continuous. And now something much stronger than that is when it's absolutely continuous. Absolutely continuous means not only every point here, every point x, you come here and it gets measure 0, but every set of measure 0 also gets measure 0, countable or uncountable. And well, of course, this is much stronger. Why? Because points, which is what's being required here, points, the set which contain a single point, this set has measure 0. So if the function is absolutely continuous variable, then it is also continuous. Why? Again, because if every point alone, if we look at the set that contains that point, that set will have measure 0 because it has measure 0, assuming that the variable is absolutely continuous, then the probability that x belongs to this set that has measure 0, it will be 0. So absolutely continuous implies continuous. And now suppose we're given a random variable with a certain description. It can be described in many different ways. It can be described through its distribution, its cumulative distribution function. We're given some random variable, and we want to check if this, if f is the density of this random variable x. Okay. So how do we check whether f is the density of x? Well, I claim that it is enough to check this only, this equality only for every x. For every real number x, we check this equality, and this is enough to say that f is the density of x. Okay. And why is that? Well, because we can, using f, we can define a measure p on R from f. How do we define that? Well, by declaring that dp with respect to the Lebesgue measure is equal to f. We can define that this measure on the real line through its density. And what we want to know, we want to know if this measure equals, if the measure p that we define this way, if this measure p, if it's equal to px. And the question is yes, the answer is yes, it will be equal to px. And why? Because these two will coincide on set A of the form minus infinity x for all x real. And why would they coincide? Well, we're assuming that we have checked this equality, which is exactly equal to this equality here when we evaluate these measures on the set A. And now we just note that the family of intervals of the real line that can be written in this form, they form a pi system. Wow, we're going back to pi system. It was not even in the plan originally. These intervals that are semi-infinite from the left and closed and finite from the right, This family of intervals, it forms a pi system, because well, when we take the intersection of two intervals of this form, what are they like? One interval is like this, the other is like this. When we take the intersection, of course we just get one of them, so it's still in this collection. It generates all the sigma algebra of Borel set, and then we can go back to that uniqueness theorem from week 1. We saw, or the beginning of week 2, maybe, we saw this uniqueness theorem that stated when two measures coincide on a pi system, they coincide on all the sigma algebra generated by that pi system. So this uniqueness theorem, it implies that this P that we define this way equals Px, and that means exactly F is a density. Then X will be a density of Px. Why? Because by definition, F is a density of P, and P is equal to Px.